This video is going to focus on carbon ion stability and regioselective chemical reactions. First, let's briefly review electrophilic addition reactions and drawing the mechanisms of reactions. First, we take the portions of the molecules that are reacting and we draw them out, including bonds to adjacent atoms and lone pairs of electrons. Second, we draw an arrow from the shifting electrons, the nucleophile, to their destination, the electrophile. So let's review the basic principles of electrophilic addition to an alkene. The double bond of the alkene acts as a nucleophile and bonds to an electrophile. An intermediate carbocation forms at the non-bonding double bond sharing, originally, carbon. A nucleophile attacks the carbon cation electrophile, forming a bond between them. Now an alkane has formed from the original alkene. It turns out that this reaction can form more than one product in some situations. In these situations, which product forms is determined by carbon ion stability, or more appropriately, how much of each product forms. Let's examine the reaction between 2-methyl, 1-propene, and hydrochloric acid, and look at both possible outcomes simultaneously. We expand the drawing to see atoms, bonds, and electrons in the functional groups. In both reactions, the double bond acts as a nucleophile and attacks hydrogen. The new bond forming fills the s orbital of hydrogen, who passes electrons to chlorine, which becomes a negative ion. In the top reaction, the tertiary carbon becomes an ion. In the bottom reaction, the primary carbon becomes an ion. The chlorine ion becomes a nucleophile and attacks the carbon ion. In the first reaction, we will end with the alkyl halide 2-chloro-2-methylpropane. In the second reaction, we end with 1-chloro-2-methylpropane. So, which actually forms? Do both form? It turns out in this reaction, only 2-chloral-2-methylpropane or tert-butyl chloride forms. But why? A reaction in which two or more constitutional isomers can form is called regioselective. The reaction we looked at is completely regioselective because of differences in carbocation stability. But if manipulated, it could become highly regioselective, yielding some of the secondary product. The tertiary carbon forms the ion so much more quickly than the primary carbon that this is the case. Let's examine why. Nearby alkyl groups decrease positive charge on a carbon atom through hyperconjugation. Recall that the lone electrons in this carbon cation exist in this p orbital, which looks like a doorknob on either side of the nucleus. And recall that there's only one electron by itself in both of these lobes. This arrangement is very unstable, which means energetically unlikely or unfavorable. However, as we add alkyl substituents next to the partially empty p orbital, the electrons of the single bonds between adjacent carbons and their hydrogens overlap with the empty p orbital, making it more stable and increasing the speed with which and the likelihood that the carbon ion will form. This is called hyperconjugation. So, a tertiary carbon ion is the most likely to form because it is the most stable. Now let's look at a highly regioselective reaction. Let's look at the reaction between 1-methyl 1-cyclohexene and hydrogen bromide. The nucleophilic double bond attacks hydrogen. Bromine ion and carbon ions form. Bromine acts as a nucleophile attacking carbon, and we get a major and a minor product. Finally, hydrogens can shift to cause the formation of a more stable carbocation. Because this is an extra step, it causes highly regioselective rather than completely regioselective chemical reactions. Shifts can also occur if ion shift causes a change from an unstable 3 or 4 carbon ring to a more stable 5 or 6 carbon ring. Here's an example of that.